Welcome back, everyone. We are going to continue our discussion today, uh, building off of where we left off last time with uh, the Boltzmann factor, um, and in particular that if you had a system which could be in one of a number of states, that the probability of being in a particular state S was 1 over z, where this is um, a normalization factor, essentially, times e to the minus beta energy of that state, where beta here is defined as 1 over kT. Again, a measure of the sort of ambient energy available in the thermal environment at a temperature T. And so this Boltzmann factor is the relative probability for a particular state of energy E relative to the other states, right? So the probability of the system being in that state, the higher the energy of your state, the less likely your system is going to find itself in that state, particularly at low temperatures. This normalization factor here, the partition function, was a function of the system and the temperature of the system, and is written down here as the sum over all of the states of the system of these Boltzmann factors, e to the minus beta times the energy of each given state. So the sum of all the Boltzmann factors is this thing called the partition function, which is the normalization for any particular state, so that the sum of all the probabilities sums up to 1. The state has to be the system has to be in a state somewhere, so all of the probabilities have to add up to 1. And again, we could think about this this partition function as a function of temperature, which describes essentially something like the number of different states that are thermally accessible by a system at temperature T. If we have a large number of identical systems, say these describe the probability for an atom, for instance, or a molecule to be in a particular state, and if we had a large number of those identical molecules or atoms, and then the average energy per atom, right? So if we have a large number n of those identical systems, and we wanted to know what's the average energy per system, the average energy per atom or per molecule in that system, then what we would do is make a energy weighted average over our system. So we would have to sum over all of the possible energy states a system could have, times the energy of that state, times the number of atoms or molecules or systems that are going to be in that state, divided by the total number of atoms or molecules or systems. And this factor here, the number of systems in our state S divided by the total number of systems, well, that's just going to be the probability of finding ourselves in that system. So that this is sum over all the states times the energy of that state times the probability of being in that state. So this is again essentially a probability weighted average energy, right? So this is the energy weighted by the probability that we're in the state that has that energy, and that will be our average energy. And we can write down the probability based on the Boltzmann distribution up here, so that the average energy, again, per state, so this is the energy per atom, the energy per molecule is given by the Boltzmann factor up here, 1 over z times the sum over all the states of E of S e to the minus beta energy of that state. And this business of thinking about the set of systems that has n total systems in it, so the set of atoms or the set of molecules or whatever, we usually call that the canonical ensemble, and the probability for each particular member of that system to be in a given state is given here by this Boltzmann distribution. So the occupation basically of each particular state S of the members of our canonical ensemble is given here by this probability function of this Boltzmann distribution. And this energy here, this is the statistical average energy per particle. So if we want to have the total thermal energy, then we just multiply by the number of particles in our system, right? So if we have a system of a mole of atoms, each of which have an average energy E bar given by this distribution up here, then the total thermal energy of the system is just Avogadro's number times the average energy per particle. Now, in this particular case, what we calculated was the average energy. But this business of weighting by probability, doing an average weighted by the probability of being in that state, well, we could apply that to pretty much any parameter or function or property that a system of a particular state would have. So we could make this more general. If you want to know the average value of some property of a system in a canonical ensemble as a thermal average value, then what you do is you sum over all of the possible states of one of those systems times the property for a given state and the probability that that state would be, or that the system would be in that state, and that's going to give you again this 1 over the partition function times the sum over all possible states of that, again, that property x for a given state, and a Boltzmann factor e to the minus beta E of S. And here we really do see the sort of the utility and the elegance of the Boltzmann distribution. It gives us basically a single tool to analyze whatever system we can quantify energy states for. If we can quantify an energy state of a system, and we can quantify that for any and all of the possible ways that that system could be configured, then we have a way of approaching the thermal behavior of that system from a statistical standpoint. For a first example, let's take a look at applying this thermal averaging to the case of paramagnetism. So we've looked at this before. Remember, this was the case where we had a system with basically two states. Either the magnetic moment was aligned with the external magnetic field, which we called the up state, or it was anti-aligned. And so we have two states, and the energy associated with the up state was minus our magnetic moment times the magnetic field strength, and the energy associated with the down state was plus the magnetic moment times the magnetic field. And so to calculate the partition function here is pretty straightforward. It's just a sum over two states of the Boltzmann factor for each of those states. So in this case, it's e to the, well, beta is, or minus beta e would be plus beta mu b, and plus e to the minus beta mu b. So this is the up state, that's the down state. And this e to the plus something plus e to the minus that same something is very close to the hyperbolic cosine, and indeed can be written as twice cosh of beta mu b. And so the probability of our paramagnetic system being in the up state is the Boltzmann factor for the up state, e to the plus beta mu b, divided by the partition function, which is, in this case, e to the plus beta mu b over twice cosh of beta mu b. And the probability of the down state, of being in the down state, is predictably e to the minus beta mu b over the partition function, or e to the minus beta mu b over 2 cosh beta mu b. So then if we wanted to know the total average energy, or the average energy of our system, it's going to be E bar, which is the energy associated with the up state minus mu b times the probability of being in that up state plus the energy associated with the down state plus mu b times the energy, or the probability of being in the down state. And if we plug in these probabilities, this is, well, first of all, minus mu b times probability up minus probability down. And we can write that as those two terms, so minus mu b times probability up was e to the beta mu b, and then the probability down was e to the minus beta mu b, and both of those over 2 cosh beta mu b. And so this here is another hyperbolic another hyperbolic function here. Just like here we saw up here, the addition of the two exponentials there gives us 2 cosh. The subtraction of the two exponentials there is related to the sinh, and indeed this whole mess here just gives us an E bar here of minus mu b times the hyperbolic tangent beta mu b. And so that's the energy per particle, and if we've got a system of a whole bunch of, if we've got an ensemble, sorry, of a whole bunch of paramagnetic systems, then the thermal energy of that ensemble is just the number of systems times the average energy per system, and that's just going to be minus n times mu b tangent, hyperbolic tangent of beta mu b. And this is indeed the solution that we derived back in chapter 3, but we took a much harder route to get there. And again, this really does illustrate just how powerful the Boltzmann statistics method here is. Again, as long as we can describe the energy states of the system, then at least in principle, it's a fairly trivial matter to grind out a partition function, grind out probabilities, and calculate stuff like this. Now, in practice, these sums may not be easy to calculate in closed form. You may have to rely on numerics or even brute force methodologies, but there is a lot of power in this technique. If we wanted to, there's another property here that we could measure, not just average energy. We could also measure the average dipole moment. So the average mu is going to be the sum over the states of mu for each state times the probability of that state, and that's going to be plus mu for the probability of being up, and plus minus mu for the probability of being down, and this gives us an average magnetic moment per system of mu tanh beta mu b, which means that the magnetization, which would be the bulk property of this, is just going to be n times our average magnetic moment, and then again n mu tanh of beta mu b. Again, a result that we clawed our way through to back in chapter 3. Again, merely a page or so got us here much quicker using Boltzmann statistics. All right, before we move on to our next application here, let me derive a super useful tool for working with Boltzmann statistics, a super useful relationship. Let's go back again to our definition of the partition function. Z equals the sum over all the states of our system, e to the minus beta energy of that state. So the sum of all the Boltzmann factors. And if we differentiate the partition function with respect to beta, then that's going to be the derivative of this, sum of over all the states of e to the minus beta to the air beta e of that state. but we can, since this is the derivative of a whole bunch of sums, well, the way we evaluate derivatives of sums is we evaluate the derivative of each term. So effectively, we can move the sum outside of the derivative there so that we're summing over a bunch of smaller derivatives. All right, so this is also the sum of the derivative by beta of e to the minus beta energy of the state. And this we can evaluate. It's just the sum for each state of minus e of that state, minus the energy of that state, e to the minus beta es. Right, so that's just the derivative of e to the minus beta, or e to the minus ax. In this case, our x is the beta and our a is this energy, and so we pulled down the energy factor there. So that is the derivative of the partition function with respect to beta. And if we multiply both sides by minus 1 over the partition function, so on the left we have minus 1 over partition function times the derivative of the partition function with respect to beta, that's going to be minus 1 over z times the sum over all the states of minus the energy of the state, e to the minus beta energy of the state. We can pull this 1 over z inside the sum and stick it underneath each of those Boltzmann factors. So this is the sum over all the states of, well, we've got the minus out front, we've still got the minus e of s, but now e to the minus beta e of s over the partition function, and that's just the probability of being in state s. And we're also going to be able to get rid of the double negative here, so we'll turn those into positives. And so what we've got here on the left is, again, minus 1 over the partition function times the derivative of the partition function with respect to this beta factor. And on the right, we've got the sum of over all the states of the energy of a state times the probability of being in that state. And this is the average energy. And so what we've got then is a relationship that says minus 1 over z times dz d beta is the average energy of our system. And we will use that a whole bunch when looking at various problems from the standpoint of Boltzmann statistics. This turns out to be a super useful analysis tool. All right, so another version or another place we can look at applying these averaging, these thermal averages, is to apply it to rotation of diatomic molecules. We've talked about the rotations of diatomic molecules a number of times, particularly in the context of the equipartition function. But here we're going to sort of take a stab at it, understanding sort of how the rotation can play out and what sort of energies we should expect to find there. All right, so for a classical system, the kinetic energy of rotation is 1/2 the moment of inertia times the square of the angular velocity. And we can write this in terms of the angular momentum, L, which is also the moment of inertia, times omega, and therefore that omega, the angular velocity, could be written as the angular momentum divided by the moment of inertia. And if we plug this back in over here, we can also write the rotational energy in terms of angular momentum as L squared over 2I. So classically, this would be the classical energy or kinetic energy of rotation for a classical rotating object. Now, to apply this to a quantized system, if we're going to talk about, for instance, molecular rotation, then we have to take this into the quantum realm. We still have rotational energy. Typically, the label here is J for angular momentum. So J squared over twice the moment of inertia. And when this gets quantized into angular momentum quantum numbers, it looks like this typically. The quantum number associated with rotational angular momentum is this J times J plus 1 times h bar squared over 2I. Or in other words, that the rotational energy in terms of its rotational quantum number here, J, is going to be J times J plus 1 times some factor here, epsilon, which is the rest of this quantum mechanical gobbledygook. And the quantum number J can range from 0 for no rotation, 1, 2, 3, and so on by integer steps. And for each level J, for each rotational energy level, or rotational level J, there are, in fact, a number of degenerate states which have the same rotational energy. And indeed, we have states that run from a second rotational quantum number, typically something like m, which can run from minus j all the way up through plus j, so that in other words there are 2j plus one of them. That would be the degeneracy or multiplicity of these states of constant j. And they represent basically different orientations of the rotational angular momentum. So for instance, again, typically you measure these relative to some, the z-axis, or you would describe these relative to the vertical axis, upon which one could conceive of aligning a magnetic field or something like that, but you don't have to. So if we have our rotation taking place sort of like so that there's a rotational angular momentum that would be vertical. We could also have the opposite sense of rotation. So have those two things rotating in the other direction, which would give us the opposite orientation. You could consider for some rotation again that there might be angles and maybe even something like that, and so on. So the angular momentum vector can be placed in different orientations relative to our z-axis here. But not smoothly. There will be quantized numbers of them, and that's basically what these 2j plus 1 degenerate states for each quantum number j correspond to. So for instance, if we look here in the book, there's a representation of the degenerate states. For j equals 0, there's only one of them, but for j equals 1, there's 3. for j equals 2, there's 5. For j equals 3, there's 7, and so on. And each of those states, at least absent an external magnetic field or something like that, would have equivalent energy, just a different orientation for the spin, or the orbital motion, the rotational motion. So when we're calculating the partition function for rotation, right, that's going to be the sum over all of the possible j's running from 0 to infinity, times the multiplicity of each j. In other words, there are 2j plus 1 degenerate states for each of those. So we have to take what's coming next, the Boltzmann factor, e to the minus e of j over kt. So the Boltzmann factor, but there are 2j plus 1 of those states with the same Boltzmann factor, and so for each j there are 2j plus 1 terms that are all identical Boltzmann factors because they're all identical energies. We can go ahead and expand out our energy as a function of j there. So again, for all j's from 0 to infinity, the multiplicity 2j plus 1, and e to the minus j times j plus 1 times epsilon over kt. And there's our sum. And depending on the kinds of energies that we're talking about, the different j sums may show up with different strengths. So for instance, here we have two representations here down at the bottom on figure 6.7 of the partition function sum that we were just talking about with each of the j terms there for different energies kt relative to the energy associated with our rotation. And you can see here that at relatively cool energies, kt over e just of 3 for instance, it's just the bottom few terms that have any power whatsoever. Whereas for the kt much larger than e, there's quite a few terms out here, and indeed the larger the thermal temperature is relative to the sort of typical quantum mechanical spacing between those rotational energy levels, the more this sum is going to start to approximate this curve, the area under this curve, or the integral. So for large temperatures, we can replace this discrete sum for kt much larger than our quantum energy epsilon. Then we can approximate the rotational partition function as an integral from 0 to infinity of this same integrand, 2j plus 1 e to the minus j times j plus 1 epsilon over kt, integrated over j, integrated over quantum number j. Obviously, for low temperatures, this whole concept is not on. It's only going to work if we're at high temperatures, if we're sort of approaching a classical limit for these rotational these rotators. All right, well, so how do we evaluate this integral? Let's slide it up there so we can see what we're doing. Let's adopt a judicious change of variables. Here we're going to let x be j times j plus 1 epsilon over kt. And therefore that dx will be, well, the epsilon over kt will come out because that's just constants. And first times the derivative of the second, so that's j times the derivative of j plus 1, which is just 1. And then the second, j plus 1, times the derivative of the first, which is just 1 again. And so this is j plus j, or 2j plus 1 out front, e or epsilon over kt dj. And what we've got in our integral here is a 2j plus 1 dj. So let's go ahead and collect this bit and move this term over to the dx side. So 2j plus 1 dj is going to be kt over epsilon times dx. So with this judicious change of variables, our partition function becomes the integral from 0 to infinity of kt over epsilon e to the minus x dx. We can pull the kt over epsilon out. So just the integral from 0 to infinity of e to the minus x dx, which is kt over epsilon of minus e to the minus x evaluated from 0 to infinity, which is which just gives us here kt over epsilon. And there, so we've got the, we know the partition function. Now, if we wanted to know, for instance, what was the average rotational energy per particle, or per molecule here, let's go ahead and use our super cool new tool that we just proved here a few moments ago. Minus 1 over our partition function times the derivative of our partition function with respect to beta. Our partition function is kt over epsilon, right? So we can write that in terms of beta. It's 1 over beta epsilon. So minus 1 over z is just going to be minus beta epsilon. D by d beta of kt over e, or kt over epsilon, which is just, again, 1 over beta epsilon here. And so running that derivative, we get the minus beta epsilon, and we're going to have the 1 over epsilon pull out, d by d beta of 1 over beta. The epsilons cancel there, and so our average energy here of rotation minus beta times minus 1 over beta squared, that derivative, which is just 1 over beta, because this beta is going to cancel with that, and the minuses are going to cancel with each other, or kt. So the average rotational energy per molecule is kt. which is exactly what we said when we talked about the equipartition function, that that we would have two rotational degrees of freedom, and because you could go, you could spin for a diatomic molecule, you could spin like so, and you could spin like so, but spinning like this doesn't do anything. So we had 2 degrees of freedom, and so we have twice 1/2 kT, and that gives us the result we just got here. Now, I should add there's one complication that we didn't take into account. All of this is valid as long as the 2 atoms in our diatomic molecule are distinguishable, so for things like carbon monoxide. But if our diatomic molecule is 2 identical atoms, things like N2, O2, H2, etc., then it turns out that if we swap our system, if we rotate our system by 180 degrees, it gets us back where we started from. And so we've sort of overcounted the number of states in our partition function. And indeed, for high temperatures, we've come very, very close to double overcounting, so that for the high temperature limit, for these kinds of indistinguishable diatomic molecules, the rotational partition function is very close to kT over 2 epsilon. At the low limit, when we're dealing with, again, just a few discrete terms there, you actually have to go in and carefully figure out which of those terms should be there and which of them aren't. And so in the low limit, you have to actually do some thinking from a quantum mechanical standpoint. On the other hand, at the low temperature limit, you can pretty much truncate the partition function after just calculating the first few terms, because you know any of these higher order terms, the Boltzmann factor is going to be super low because the temperature is low, and therefore the probability of being way up here in one of these funky states is essentially 0. And indeed, since we've brought up the equipartition function, let's in fact finally get around to proving the equipartition theorem. We haven't really proven it, we've just sort of stated that it is useful for systems with quadratic degrees of freedom, but now we have, with the Boltzmann statistics, the tools to finally prove this statement. So first of all, a system with a quadratic degree of freedom, that's any system that you can write down the energy here in terms of some parameter q, which is something like a generalized coordinate. So think of Lagrangian mechanics. We're talking about things like position, momenta, angular momentum, the generalized coordinates that you usually use in Lagrangian mechanics. So anything we can write in that term, and then there is some constant here, c times q squared. So this is a system with a quadratic degree of freedom, where we could write down, in this case, that 1 degree of freedom q, and write down something of that in that form. So we're going to, in the context of Boltzmann statistics here, we're going to treat this single degree of freedom as our system, and calculate the average energy in that degree of freedom. And to start with, we're going to assume that we've got a classical variable, something like position, momentum, angular momentum, something like that, and that we could, so that the values of Q can vary over a large range continuously. And indeed, we're going to imagine taking that continuous range and breaking them up into very, very small delta Qs so that we can count the states of this semi-classical system. And so the partition function then is going to be the sum over all of the different Qs times e to the minus beta energy of Q, and that's going to be the sum over all Q's of e to the minus beta and C, our constant, times Q squared. And then we're going to multiply by delta Q and 1 over delta Q. All right, so we're going to keep the same, we're not changing anything by doing this, we're just doing some rewriting and mathematical chicanery here. E to the minus beta CQ squared delta Q. And again, now we're going to take advantage of the fact that we are assuming that these delta Q's are very, very small, that we have a parameter in a sort of a semi-classical limit here. And since the delta Q's are very, very small, then we can turn this discrete sum into an integral like so, that the partition function becomes, we still keep this 1 over delta Q out front, but now we're integrating over all the possible values that Q could take from minus infinity to infinity of e to the minus beta CQ squared dq. All right, so how are we going to evaluate this? We're going to, again, do a change of variables here. We're going to let x equal the square root of beta c times q, which may seem slightly weird, but if we do that, then our dx becomes the square root of beta c times dq, which we can then rewrite as dq equals dx over the square root of beta c. And so our integral here then becomes, we still have the 1 over q out front, but our dq is going to turn into a dx, and so there's a 1 over beta c that we can also pull out of that integral. We have the integral from minus infinity to infinity of e to the minus x squared dx. And this is this is a Gaussian integral. It's a integrand that does not integrate well into standard functions, or does not differentiate well, or anti-differentiate well into standard functions. So we can't just write down the generic value of that integral, but it evaluates in closed form over an infinite interval here. The proof is actually of this is a fairly simple proof in your appendix for how to prove what the value of this Gaussian integral is. But it all comes to a value of the square root of pi. And so our partition function here then is 1 over q, delta q, times the square root of pi over beta c. And we're just going to call that a different constant, capital C, times beta to the minus 1/2. And again, this capital C then is square root of pi over little c divided by r delta q. All right, once we've calculated the partition function like we just have, now to calculate average energies, we just do the following. So the average energy of our system, which again, remember, is our single quadratic degree of freedom, is again just minus 1 over our partition function times the derivative of the partition function with respect to beta. There's that super useful tool again. And 1 over z, that's just 1 over capital C or big C times beta to the minus 1/2 times the derivative with respect to beta of, again, C beta to the minus 1/2. And if we evaluate that derivative, again, the minus 1, oops, we lost our minus sign there, our minus 1 over C beta to the minus 1/2. Derivative of that's going to give us a minus 1/2 C beta to the minus 3/2. The two C's cancel. The minus signs cancel. And our average energy per quadratic degree of freedom is 1/2 beta to the minus 3/2 over a beta to the minus 1/2 is a beta to the minus 2/2, or a beta to the minus 1, which is 1/2 kT. So the average energy per quadratic degree of freedom is indeed, as we have been saying all semester long, 1/2 kT. This all works as long as the assumptions that we've been making through here hold up, and the assumption that we made through here that had to hold up is that we're in a classical limit, that we're at least in a semi-classical limit, that the delta q's can be seen as small. In other words, that the spacing between the various quantized energy levels of our system is much, much smaller than the typical quantum numbers for that system. As long as we're not down at the quantum limit, down at the small number limit for our system, then the equipartition rule will result. In particular, if we're at relatively high temperatures, then that should be fine. But when we try and extrapolate the equipartition function down to low temperatures, this is all going to fall apart, because the approximation that we can treat this as a semi-classical thing, that we can turn this discrete sum into an integral of very small dq's, doesn't work when we've only got 3 terms and our dq goes from 0 to 1 to 2, right? Those are not small jumps. We cannot approximate that as an integral. So the equipartition function will fail at low temperatures, and when we talked about the equipartition function back at the beginning of the semester, back at the beginning of the book, back in chapter 1, that indeed was part of the discussion, that the equipartition function works fine for sort of terrestrial room temperature kinds of things, but does not work very well at low temperatures. All right, one last example that we're going to do here with the Boltzmann thermal averaging. And that is to look at the so-called Maxwell distribution. So what the Maxwell distribution is, here we can have a picture of it. The Maxwell distribution is a distribution, it's a probability distribution which shows you the relative probability of finding an object or the molecules or atoms of an ideal gas at a particular speed, moving at a particular speed. So this is the relative probability as a function of speed. And you can see it's sort of got a bell-shaped curve. There's a maximum peak value here. And that if you take any area under this curve, that'll tell you the relative probability of having a speed between here, for instance, v1 and v2. The area under this curve, that would be the relative probability, or the probability of finding a particle in an ideal gas at in that that temperature, or in that velocity range, in that speed range. All right, so the probability again of finding a particle in an ideal gas, a molecule, or an atom at a speed between v and v plus some little dv. This is the distribution function d as a function of v dv. So that's sort of the definition of this distribution function, which is this scripty d. Which means that the way that you would calculate the probability of finding a velocity between a v1 and a v2, then that's going to be the integral of from v1 to v2 of this distribution function d of v dv. And this is how this distribution function, how these distribution functions are meant to be used. They're always meant to be used in the context of some sort of an integral over this parameter space. And so the way that we're going to work this again is, you know, the probability is or this distribution function here. Clearly, it's going to be proportional to the probability of a molecule having velocity v where v is a vector velocity whose speed corresponds to this this unvectored speed v. But it's also going to depend on the number of velocity vectors at that particular speed. So the number of vectors at speed v, right? Because the more vectors that have the same velocity, or the same speed, the more velocity vectors that have the same speed, the larger velocity. So for instance, speed 0, we'll see you have a pretty high probability of any particular given molecule being at speed 0. But the number of vectors that correspond to speed 0 is 1. There's only one speed 0 vector, whereas there are more vectors for various speeds. This first term is the one that we're familiar with now. It's proportional to the Boltzmann factor, right? So this is going to be proportional to e to the minus, in this case, kinetic energy, translational kinetic energy, mv squared over 2kt. All right, because the energy of a given velocity state here is going to be 1/2 mv squared. Therefore, the probability of a molecule having a velocity v is going to be proportional to this Boltzmann factor, e to the minus mv squared over 2kt. And again, you can see that 0 should be a very, very popular choice for probability. There should be a high probability that a molecule has close to 0 speed. But again, at 0 speed, there's only one vector with 0 speed. If we imagine a velocity space here. That's relatively easy to do. So a three-dimensional velocity space. So we've got a Vx and a Vy and a Vz. The components of whatever our velocity vector is going to be somewhere here. Well, if we have to imagine that all those velocity vectors are moving at a speed of v, then they have to lie somewhere on a spherical surface here of radius v. And so the number of vectors which have the same energy, same kinetic energy, at that speed v, that's going to be proportional to the surface area of this sphere. So that's going to be proportional to 4 pi v squared, the surface area of a sphere. In this case, a sphere in velocity space, but a sphere nonetheless. So the two key components here of our distribution function are a Boltzmann factor with an e to the minus kinetic energy over kt, and the surface area of a sphere in velocity space 4 pi v squared, so that combining those two, we get a distribution function. V, d of v, is going to be some constant times 4 pi v squared times e to the minus mv squared over 2kt. Right, so this over here, that's the Boltzmann factor term. This is the surface area term, and this is some constant. Now, what is that constant? We can find that constant by saying that if we take and integrate over all possible speeds that a particle could have from 0 to infinity, dv dv, then it has to be 1, because the particle has to have some speed somewhere between 0 and infinity inclusive. Now, let me just state as a caveat, obviously we are ignoring relativity here. Nothing about this derivation will work for relativity. And so this notion that we're able to integrate all the way out to infinity, take with a grain of salt. But as long as our temperatures are not relativistic, then corrections here won't have to be relativistic either, because when we start to get to infinite or very large velocities, this 1 over kt term is going to be very, very small. So the Boltzmann factor will suppress anything out in the relativistic regime as long as we are not at relativistic temperatures. At extremely high temperatures, then this whole Maxwell distribution doesn't hold up, and you have to approach things from a relativistic standpoint to begin with. It can be done, it just comes out very different. All right. So let's go ahead and do this normalization. 1 is equal to, we can pull the 4 pi out, and we can pull this constant c out, and then we're left with the integral from 0 to infinity of v squared e to the minus mv squared over 2kt dv. And we're going to let x, we're going to do another substitution here. X equals v times the square root of m over 2kt. So that dx then is dv times square root of m over 2kt, which will mean that dv equals dx times the square root of 2kt over m. And also x squared will be mv squared over 2kt, and v squared, therefore, 2kt over m x squared. All right, so with all that in mind, let's plug things back into our integral here. We still got the 4 pi c out front. The integral from 0 to infinity. Our v squared turns into 2kt over mx squared. Our e to the minus thing turns into just e to the minus x squared. And our dv turns into dx times 2 square root of 2kt over m. So we substituted in for each of those three chunks, this chunk, and that chunk. Let's pull a whole bunch of constants out front. So this gives us 4 pi c again, but those two constant terms come out, and indeed they combine. They're 2kt over m, and I square root of 2kt over m, so 2kt over m to the 3 halves. And now we've got the integral from 0 to infinity of x squared e to the minus x squared dx. This is another one of those integrals, kind of like the Gaussian integral, that you can look up in tables. This one is also discussed in the back of the book. You can solve it fairly quickly, or you can reduce it fairly quickly back to the Gaussian solution by doing some integration under differentiation under the integral sign. But again, you can just look this up. Square root of pi over 4 in this case is what that integral turns out to be. So 1 equals 4 pi c 2kt over m to the 3 halves, and square root of pi over 4. The 4 cancels with this 4, and what we're left with is c pi to the 3 halves 2kt over m to the 3 halves equals 1, or in other words, our constant c is m over 2 pi. We can pull the pi into this 3 halves business, kt to the 3 halves, such that then our total Maxwell distribution then is equal to m over 2 pi kt to the 3 halves times 4 pi v squared e to the minus mv squared over 2kt. So this is the Maxwell distribution. Named after James Clerk Maxwell. And again, we've got a Boltzmann factor here, the surface area of a sphere in velocity space, and a normalization constant. This is the only hard part to memorize, what the normalization constant is. The rest of this makes intuitive sense. What if we want, let's learn some things about this distribution. So this distribution is going to have a peak, right? Again, if we look at the distribution here, the Boltzmann term peaks. The Boltzmann term would give us lots of probability down here, but the number of states term drops off for small velocity, and so there's a fall off here, and the fall off at high velocity is due to the Boltzmann terms at high, or not populating velocities for modest temperatures. To find where that peak happens, we could just take the derivative of our distribution with respect to velocity and search for the place where that derivative is 0. So That's the place where we're going to have our peak, the most likely speed for a given temperature. And we can say, all right, so that's going to be this distribution function. We'll go ahead and take the 4 pi and the c. I'll just write that again as c. So 4 pi c times the derivative with respect to velocity or speed of v squared e to the minus mv squared over 2 kt. It equals 0, so we can in fact get rid of those constant terms out front altogether. So it's just this derivative which has to go to 0. This is a composite derivative, so we're going to take the first term here, v squared, times the derivative of the second, d by dv of e to the minus mv squared over 2 kt. And over here we're going to take the second term, our Boltzmann factor, e to the minus mv squared over 2 kt, times the derivative of the first term, d by dv of v squared. So this is just breaking up that product, or that derivative by the product rule. This derivative is trivial, right? So this is e to the minus mv squared over 2 kt times 2v. This derivative over here gives us a v squared times minus 2 mv over 2 kt e to the minus mv squared over 2 kt. Whoops. And so 0, we have m minus mv cubed over kt e to the minus mv squared over 2 kt plus e to the minus let's see, e to the minus mv squared over 2 kt times 2v. Let's go ahead and pull this first term over the left. So, and divide both sides by the Boltzmann factor term. So mv cubed over kt equals 2v. And we can cancel that v with one of those and leave us with just 2. So that v squared, we're going to label this peak velocity, is 2 kt over m. So that v peak then happens at the square root of 2 kt over m. So that's where that peak velocity in that distribution takes place. We could also calculate the average velocity in our distribution. So the average velocity, well, that's going to be the integral from 0 to infinity of velocity times our distribution function dv. Right, so if this distribution function dv, if that's the probability of having speed v, then if we want the average speed, we have to take v times that probability and integrate over all of the possible speeds. Right, so this is that Boltzmann averaging. This is that thermal averaging again. So again, we can plug in our distribution here. Right, so that gives us 1 over 0 to infinity of m over 2 pi kt to the 3 halves 4 pi v times the v squared gives us a v cubed in here, e to the minus mv squared over 2kt dv. Pull out all the constants in front that we can. So that's going to give us the m over 2 pi kt to the 3/2 and a 4 pi out front, and then we've got the integral from 0 to infinity of v cubed e to the minus m over 2kt times v squared dv. So I wrote it like that because this is an integral of the form 0 to infinity of x cubed e to the minus ax squared dx. And again, you can look this up in integral tables. This is not a calculus course. This is not about finding the way to do all these integrals by clever math tricks. 2a squared, 1 over 2a squared is that. So in our case, the a is this business there. So our average velocity then is m over 2 pi kt to the 3/2 times 4 pi times 1/2 times 2kt over m squared. The halves cancel. That's going to give us 2kt over m, or kt over m squared, and here we have kt over m to the minus 3/2, and the pi's are going to cancel there, and if you do this all correctly, you get the square root of 8 kt over pi times m, which we can write here as a slightly different form. I'm going to write this as the square root of 4 over pi times the square root of 2kt over m. Why did I do that? Well, because the square root of 2kt over m is our v peak. So this is 2 over the square root of pi times v peak, or in other words, that the average velocity is about 1.13 times the peak velocity for a Maxwell distribution. We even, back at the beginning of the semester when we talked about the partition function, or the equipartition theorem and things like that, we talked about the relationship between the average velocity. That's what we actually wanted to calculate or talk about back then. Well, we couldn't calculate the average velocity back then because we didn't have this distribution function tool. But instead we related it to what we could calculate, which was the root mean square velocity. So let's go ahead and look at what the root mean square velocity would look like, and we can relate that back to things. So to calculate the RMS velocity, well, what is RMS? Well, root mean square means literally the square root of the average of the velocity squared, the average of the speed squared. So we'd have to calculate v square bar, the average of v squared. Well, again, that's going to be the integral from 0 to infinity of v squared times our distribution function dv. And so we could plug this in again. We can do all this business again. This is going to give us again m over 2 pi kt to the 3/2 and 4 pi out front. V squared, and then the other v squared gives us a v to the 4th term, and e to the minus mv squared over 2kt dv. And again, we have this same factor we had over here. We could rewrite this as m over 2kt, and that's going to give us an integral of the form 0 to infinity of x to the 2n. In this case, n is going to be 2, e to the minus ax squared. And that integral, I encourage you to look this one up on a table because it's a little bit obscure. It's basically a whole bunch of integration by parts and a recurrence relationship and all sorts of fun stuff like that. But 2 to the 2n plus 1 square root of pi over a to the 2n plus 1. Probably it could take a whole lecture just to derive that one particular integral, but thankfully integral tables do exist. This is valid for positive a or for a greater than 0 and also for n positive. In our case, n equals 2 and our a equals, again, this m over 2 kt. And so if we take this and plug it back in, then our integral here becomes 4 factorial over 2 factorial times 2 to the 5th square root of pi over m to the 5th 2kt to the 5th. And so that gives us 4 factorial is 4 times 3 is 12 times 2 is 24. And this 2 factorial, well, that's 2 times 2 to the 5th. That's going to give us 2 to the 6th, or 64. So this is 24 over 64. There's a square root of pi, and 2kt over m to the 5 halves. That's what comes out of this integral, and so that our average speed squared is m over 2 pi kt to the 3 halves, and 2kt over m to the 5 halves, and 4 pi and a root pi, and 24 over 64. And if we take the 4 and multiply it in there and simplify all the pi's and the 2kt over m's, what we get here is just a factor of 2kt over m and 96 over 64, which reduces to 3 halves times 2kt over m. So that, in other words, the average of speed squared is 3kt over m, which is good because that's the same result we would have gotten from equipartition, that if you take this, you go m v squared average over 2, that's our average energy. That's going to be 3 halves kt. So this agrees with that, and therefore I'll go ahead and write that back over here, that our VRMS is just going to be the square root of this 3kt over m. And I'm going to write that as square root of 3 halves times the square root of 2kt over m. And that's again relatable back to the peak velocity, that this is 3 halves v peak, square root of 3 halves v peak, or in other words, about 1.22 times our peak velocity. And my pen is dying. 1.22 times our peak velocity. So the peak velocity is the smallest, the average velocity is a little bit larger, and the RMS velocity a little bit larger than that. About 13% larger than the peak velocity here, about 22% larger than the peak velocity there. And the relationship between average velocity and peak or RMS velocity is that the RMS velocity is, or that the average velocity is about 93% of the RMS velocity. That V average is about 0.93 times VRMS. So RMS isn't a terrible approximation for average velocity for a Boltzmann or for a Maxwell distribution. Now, what is the Maxwell distribution? Again, this is the distribution of speeds that would be relevant for ideal gases in a non-relativistic limit. All right. That's all for this time. Next time we will look at a different aspect of Boltzmann statistics, relate it back to the free energy, and finally go back and look at ideal gas.